Okay, let's go over the algorithm for Newton's method, and then we will do an example after this, because this algorithm is not going to take very long. This is actually a really easy thing to code up. It's pretty short and usually is pretty easy to do. Remember what we're trying to do. We want to find a root. That's what we're looking for. So we want to have f of x equal to 0, and f, you obviously have to be able to find a derivative of that function because we do need it in our calculation. We also have to give it this initial approximation, which I'm going to call XO. All right. So our inputs, we're going to have XO, our initial guess, a tolerance, it tells us how accurate we want it. The max number of iterations, again, that is to keep us from going into an infinite loop. We need our function f of x, and then you need to be able to get the derivative of f of x. Now, what we're going to get out of here is our approximate solution, which I'm going to call x, or we'll get a failure message. Okay. So now what we're going to do is we're going to set I, and it's going to go from 1 to the max number of iterations. Okay. And we'll stop before NO if we meet our tolerance. All right. So we'll set this, and then we're going to do these 3 steps right here. So step 2, we're going to use that iteration formula for Newton's method. That should look familiar to you. All right. And after that, once you do this calculation, you're going to get an x value, right? That's going to give you where we're crossing that x-axis. So that'll be our estimate of the root. So what we're going to do then to check and see if we've got enough accuracy is we're going to take the absolute value of x minus xo divided by xo, see if it's less than our tolerance. If it is less than that tolerance, we're going to output x. Okay. Otherwise, we're going to update that initial guess, xo. So now we'll say xo is equal to x, and it's basically just going to continue doing this until this condition is met or we hit our max number of iterations. If we hit the max number of iterations, we'll need to display some sort of failure message. All right, so that's the basic algorithm. It's really short, and in MATLAB, it's really easy to code up. All right, so let's go ahead and we'll look at example 2. And let's see what this is. So for example 2, what we're going to do is we're going to use Newton's method, obviously, to find a solution accurate to within 10 to the negative 4. This is the tolerance. And then we want to do that for this cubic function. All right. So we got x cubed minus 2x squared minus 5 is equal to 0. And then we have this interval from 1 to 4. Okay, so obviously this is a cubic function. It's going to have 3 roots. And you're going to have to specify, which one you're looking for. Okay, because you would have to run this method 3 different times to get the 3 roots. All right, so we're looking for the one in this interval. And my initial guess, I just said it was 2 because that falls in that interval. All right, so that's what we've got to work with. Now, before we get started, let's go ahead and find f prime of x. This is f of x right here. All right, so it's just that function. And then f prime of x, we need to find the derivative of that. So that's pretty easy to find. So we'll have 3x squared. And then we'll have minus 4x. All right, so there's our derivative, easy to find. Now, what are the problems with this method before we go on? Sometimes it's not always easy to find the derivative that you're looking for. All right, so this one was easy to find, but sometimes that's not the case. So in the next method, we'll cover a method where you don't need to have a derivative. All right. Now let's go ahead and make up a table, kind of like what we did with the bisection method. So let's make a column for I. Let's do our initial guess, XO. Then let's do X. And then let's have one to check the tolerance. All right, so the absolute value of x minus xo over xo. And now we'll just go through and fill this out. So the first time through, I is going to be 1. XO, that was given, that was our initial guess, so that was right here. So that's going to go to 2. And then now what you need to do is just use the iteration formula. So if you remember, that's it right here. So I have XO minus f of XO over f prime of XO. All right, so that's it. And if you want, we can write this down. There you go. So that's the equation we'll be using. So let's go ahead and fill that in. So we're going to have 2 for XO and then minus. We're going to take our function right here, plug in 2 everywhere we see x. All right, we'll have 2 cubed minus 2 times 2 squared minus 5. Put that over f prime of 2. So I have 3 times 2 squared minus 4 times 2. And that is 3.25. Okay. Now we're going to take this, plug it in here. All right, so x is 3.25. We'll subtract 2, divide by 2, and we get 0.625. And that's basically it, right? It's not too hard to do. Now this is obviously still bigger than this tolerance. All right, because I want this value here to be less than this. Okay, so we're going to go again. And now what we do, if you remember, let's look at this. We didn't meet this criteria, so we go down to step 4. Now we just need to update XO. So we're just going to replace our value for XO, and now it's going to become 3.25. And then you just repeat the process, so that's basically it. So it's really pretty simple, but it actually works really well. So it's 3.25, and then we'll just plug that into our 2 functions here. All right, so let's cube it, and then minus 2 times 3.25 squared minus 5. Put that over 3 times 3.25 squared minus the 4 times 3.25. And now what we get for this whole thing is 2.81104. All right. And again, just to let y'all know, you always want to carry out digits. You don't want to cut it off after 2 digits past the decimal place. All right, the more you have, the better. Otherwise, you're going to lose accuracy. So let's take this number, plug it in over here, check out the tolerance, see if we meet it. Okay, so now we've got the 2.81104 minus 3.25. Put that over 3.25 and we get 0.1351. Now this one is better than this one, but it still doesn't meet our requirement. So we're going to have to go again. So let's put I equal to 3. And now we're just going to take this value and it's going to become XO. Okay, so now we've got that. And basically now you just repeat that process. So here we'd have 2.81104 minus, and then after you plug it into f of x, you get 1.409. Take this 2.811 number, plug it into f prime, you get 12.4617. And then that gives you 2.69797. Okay, now we want to check this. So we do our absolute value. So we'll take our new x value, subtract our original x naught, or XO. And now you're going to get 0.0402. So it's getting better, right? Notice how this is getting smaller and smaller. That's because you're zeroing in on your root. Okay, so that's why this distance here between the two gets smaller and smaller. So now you'll just keep going with this process. For the next couple lines, so I'm just going to write out the values. So this now becomes XO. So move that over here. And then when you do this calculation with this value, you'll get 2.69068. And then that will give you the tolerance over here, or not the tolerance, but the value of 0.002703. This still doesn't meet tolerance. So let's go one more time and hopefully we'll be done. Now this becomes the new XO. So we have 2.69068. And then now when we plug that in to our iteration formula, we get 2.69065. Okay. And then finally over here, you'll get 0.000011. And this is what we want. So that looks good. So that means we're done. Okay. And that means that this right here is our estimate. So let's just write down that the solution estimate is 2.69065. So this would be your answer. All right, so that is your root in the interval between 1 and 4. Now, if you were to actually go through and plot this function and find the root, the actual value is 2.690647448. So you can see, I mean, that's pretty close. All right. So this method is actually pretty accurate as long as you give it a decent initial guess. Like I said, I mean, if you're way off on the initial guess, it's not going to be as accurate. But if you give it a decent guess, it's pretty accurate. It tends to converge to a solution fairly quickly, and it's really easy to code up. The only issue with it really is finding the derivatives sometimes. Okay? So that's the Newton's method, and we will do one more example with Newton's method in the next video. So I will see you guys then.